Hello everyone and welcome back again to the linear algebra component of the Calculus and Linear Algebra series. In the last video we introduced this idea of a kind of algebraic formula for the cross product or vector product, as well as talking about and proving the distributive property of the cross product with the addition of vectors. And in this video I want to introduce two new concepts and understand their geometric meanings, known as the scalar triple product and as the vector triple product. So we'll start off with a definition of the scalar triple product. So this can be found in the notes as well, but I'll write explicitly what the definition is here. So we start off by saying we take let u, v, and w be vectors in R3. We need to have R3 again because we're going to talk about something with the cross product in. So then the scalar triple product is defined as, we write it as u dotted with v cross w, simply written in this way. And why is this useful? Well, this quantity, this scalar triple product, has a kind of relationship to geometry. So much like when we saw the norm of the vector product, we saw that that was equal to the area of a parallelogram spanned by the vectors v and w. This thing, the scalar triple product, corresponds to the volume, or if we take the norm of this thing, that gives us the volume of a parallelepiped spanned by the vectors u, v, and w. In general, it would always give you the volume without taking the norm, but the volume might be negative depending on the orientation of those vectors. So if you take the overall norm, that will ensure that thing is positive, and we understand volumes to be positive. So what do I mean by this kind of, how do I picture this diagrammatically? So I'll do my best to draw this. So I'll maybe write this now as kind of XY coordinates, like so. If we imagine kind of going into the page, we can dash this along and say this is something like our vector u. And going along here, let's say is our vector v. And if we take then our another vector up here, say we can think of as w, then if we kind of piece this together, so if we kind of imagine u goes further back like this, and then we kind of have a blue vector like so, another blue vector, we have our yellow vector like this. Hopefully you're seeing the picture here. Draw this like so. We're going to have another red vector going like this up here. We have another red vector like this. It's getting a bit slanted there. Maybe I'll extend this blue vector. And then finally our yellow vector like this. So maybe this blue vector needs to be slightly further along. Okay, so what we're saying here is that whatever this kind of region is in the middle, we've missed one vector here. What vector have we missed? We've missed the red vector again on the back. So kind of write that like that. Okay, so this is kind of what we think of as our parallelepiped, and the thing inside, we can write this as v. So the volume of this parallelepiped is equal to the norm of u dotted with v cross w. In general, we don't really need to take, well, you take the norm just to ensure that it's always positive, because depending on the orientation that you pick, it could turn out that this results, or this vector, this quantity in here, results in a negative quantity. So taking the norm just ensures that it is indeed positive. So that's a geometric interpretation of the scalar triple product. So if you ever want to find the volume of this thing, you can simply take the scalar triple product of these three vectors. So let's do an example of this, how we would take the scalar triple product. So in the notes, we have u is written as 1, 2, 3. V is the vector 0, 0, 1. And W is the vector 0, 1, 0. Then the scalar triple product, or alternatively we could say the volume of the parallelepiped spanned by U, V, and W. So the scalar triple product of the three vectors is given by the following. It's going to be written as U dot V cross W. We can find V cross W as simply, well, we know just according to our right-handed orientation that this thing effectively is the K vector and this thing is J. So if we do V cross W, that is in other words K cross J, which is the same as I, also minus I in that situation. So we get minus 1, 2, 3 times minus I, which is 1, 0, 0. In other words, the dot product with that, which is minus 1. So we see exactly this reason for why we need to take magnitudes if we want to talk about the actual volume, because we've got a negative answer here because of the orientation that was picked. If the left-handed orientation was picked, then the cross product would have resulted in this thing being positive and not negative. But in this situation, we took a right-handed definition of an orientation, which meant that the cross product was negative of these of V and W, and therefore, in order to find the volume, we would need to take the magnitude. And much like before, there's some kind of useful properties that we can write down of the vector triple product, of the scalar triple product, that allow us to make computations maybe slightly more tolerable. So in this situation, we've let U, V, W, and R be vectors in R3. Then we have the following things holding. The first one is we say that U dot V cross W is equal to W dotted with U cross V, which is equal to V dotted with W cross U. So you can prove all of these. I leave as an exercise for you to prove yourself. They're not that difficult to prove, just a little tedious. Substitute in, U as U1, U2, U3, V as V1, V2, V3, W as W1, W2, W3, and calculate these expressions individually and check that they are indeed equal. So the next one we have is that U dotted with V cross W plus R is equal to U dotted with V cross W plus U dotted with V cross R. Again, fairly tedious but easy to check, so check these yourself. And we have kind of a similar version now for scalar multiplication. So we have U dot V cross W is equal to CU dotted with V cross W, and then we can kind of take that inside, so we can also write that as U dotted with C times V cross W, which is the same as U dotted with V cross CW. And that just follows mainly from some properties of the vector product. So the proof of those, as I say, you can prove those yourself. They're not that hard to do, just a little tedious. So the proof is an exercise to yourselves. So do that for yourselves at home. Make sure you do that after you're kind of watching this video. And then that leads us to the kind of next idea that's going to be useful, which is known as the vector triple product. Why is this going to be useful? Well, the vector triple product is more for a calculational point. We don't really think of it, well, I don't think of it geometrically. So in this situation, we have let u, v, and w be vectors in R3, then the vector triple product is defined as u cross v cross w. So at this point, it's not really particularly profound to talk about the vector triple product, because it's simply saying that we're taking the product or the vector product of three vectors in R3. Where it's going to be useful is when we start talking about this theorem known as Lagrange's formula, because it might be very common that in lots of scientific disciplines that you might end up with lots of cross products or vector products of vectors. But you might want, this is quite computationally intensive. Just doing the cross product between two vectors is a bit of a pain. So doing it for three vectors and four vectors and so on is even more of a pain. So is there a way in which we can write the vector triple product in terms of some things that are easier, say like the scalar product? And this is what leads us to Lagrange's formula, which is effectively a quicker way of finding the vector triple product. So that's why it's useful. We just give it a name in this situation. But the really useful thing is relating the vector triple product to this other relation, which is Lagrange's formula. So that leads us to our kind of final point. Then we'll do an example. So our theorem here is for Lagrange's formula. We let u, v, and w be vectors in R3. Then we can just write that u cross v cross w, in other words, the vector triple product of u, v, and w is equal to u dot v times w minus u dot v, u dot w times, let me write that out again. That's equal to u dot w times v minus u dot v times w. Okay. So as I've said here, I can write my kind of the idea of the proof here that's also in the notes. But you can kind of do the others yourself. So we're not going to look at every single component of this, right? This thing on the left-hand side is a vector, and the thing on the right-hand side is also a vector. So if we just, and because of kind of the symmetry of how the kind of first component relates to the second component, which relates to the third component, I'm just going to show that it works for the first component, and I'll leave yourselves to calculate for the second and third component. So we're just going to show that the first component of this thing is indeed equal to the first component of this thing, and therefore you can deduce the rest, that the second and third component are the same, so you can do those calculations yourself at home. They're a little tedious, but again, fairly easy to do. So we define u to be u1, u2, and u3, v to be v1, v2, and v3, and as you might expect, we let w equal w1, w2, and w3. So expanding the left-hand side, expanding this cross-product formula, what you should find is then the first component is given by, so if we expand and look at the first component of this thing, we get u2 times v1 w2 minus v2 w1 minus u3 v3 w1 minus v1 w3. And what we can do here now is we can factor out the term v1 in the first expression and w1 in the second expression. Why are we doing that? Because in this side we're only going to look, we're trying to compare it with the first component of this thing. Well, the first component of this thing is going to be multiplied by the v1 component, and the first component of this thing is going to be multiplied by the W1 component. So it's useful to do that. So if we take out the factor of V1, we see that V1 appears in here, so we get U2 W2. And then we get, with another V1 here, we've got W3 U3, but with a minus times by a minus, so that's plus U3 W3. And then we're going to get plus, we take out our factor of W1, which in this situation, well actually take the minus sign outside the front, because we're looking here at a minus factor. We see that we get V2 times U2 with a minus sign, so the overall thing inside is positive. So we get U2 V2. And on the other one, we have V3 U3 times by a minus sign. In other words, we get plus U3 V3, which we can write as V1 times U1 W1 plus U2 W2 plus U3 W3. And we see here what we've done is we've added on this U1 W1. So in other words, we want to take away V1 times U1 times W1, but we can take that into this other expression and factor out the W1. So then we'd get W1 times V1, or let's write it the other way around. We can write it as U1 V1 plus U2 V2 plus U3 V3, which is equal to V1 times U dot W minus W1 U dot V, which is exactly this expression that we have up here, where we've got the kind of first component of V and the first component of W, which is V1 and W1. So a similar calculation can be done for the remaining components. So check this for yourself. Check indeed as well that the expansion of this thing and looking at its first component indeed gives this expression here. And then hopefully the other stuff follows from that. So that's something to do yourself at home. So I'll put a kind of box here to say that that's finished the proof. So what's an example of how and where's this going to be useful? So let's look at an example of where Lagrange's formula can be used for the vector triple product. So in this situation, we're going to have, like before, we're going to take the same vectors, like u equal 1, 2, 3, v equal 0, 0, 1, and w equal to 0, 1, 0. In other words, this vector here is k and this vector here is j. Then the vector triple product of u, v, and w is given by, we can just write it as u cross v cross w. So we can write this as 2 times 0, 0, 1. Why have we got that? Let's just look at our formula above. So we take the vector v. So our vector v here is this 0, 0, 1, which is what we got here. And then the thing in front was u dot w. So u dot w is this one dotted with w, which in other words just gives this second component, namely the number 2. And then the second piece I've written as minus 3, 0, 0, 1. So let's check that with our formula. The second piece was the vector w times by u dot v. So if we have u dot v just isolates the third component here, which is the number 3, times by the vector v, which is the vector 0, 0, 1. Sorry, no, the vector 0, 1, 0. Because we're multiplying it by the vector w. Okay, and if we take them together, then we simply get what? We get 0 minus 3, 2 as our overall answer. So why was this useful? Because if I had to compute this thing doing the kind of full formulas for the cross product and vector product, it would take a lot longer, plugging all these expressions in. Alternatively, I guess you could spot straight away that v cross w in this situation is equal to minus I. So that can kind of give you a simple way of doing that and then cross that with u. But in this situation, it was very simple to just take these dot products and multiply them by these vectors. And in general, it's going to be much more calculationally less intensive to use Lagrange's formula to find vector triple products than kind of expanding them in general. So that's where we're going to finish off the topic of vector products this week. And in fact, next week, what we're going to move on to is we're going to start talking about things like equations of planes, equations of lines, and how to calculate distances or shortest distances between lines and points, planes and lines, and between two planes and things like this. So again, I remind you to read the notes on this and attempt any of the proofs that were left as an exercise, and also try any of the problems in the module handbook relating to the material discussed in this video. So thanks very much for watching, and see you in the next video.